Good day, folks. Here's another electrostatic question. Two charged sphere R and S are both stationary. It's a very important point. That means the F net is equal to 0. They're at rest. That's what it means. The acceleration is 0 as well. Alright? On a smooth, that means no friction. Insulated surface inclined with 25 degrees to the horizontal sphere S has a mass of 0.01 kg carrying a charge of what? Negative nanocoulombs and connected to 0.03 meter long light insensible string attached to point P at the top of the incline. Now guys, that statement is referring to this one. This one is attached by a string there and it's stationary, it's not moving there, and at the distance from where it's attached it's 0.03 and it's negatively charged. That's what is important there, and it's on an incline as well. Right now it says a sphere R, we're referring to this one, carrying a charge of 5 nanocoulomb, which is it's positively charged, is held. Also it's held, that means it's at rest. That means the F net is equal to 0, the acceleration equal to 0, held in such a distance, in such that the distance between the centers of sphere R is shown in the diagram below. So we are told there is a distance between them, the R and S. The distance is R, is unknown, the distance. But what you need to know, there's an electrostatic force between the two, right? Okay. Let's answer the question. It says a sphere R, the statement sphere R and S exact an electrostatic force of magnitude of 1.2 newtons, 1.2 times 10 to the power negative 3 newtons on sphere S. So these two, they're exacting a force on each other. That force as we are told here, R is exacting a force on this one, but S is exacting the same force on this one. This Newton's third law, but in opposite direction. State Coulomb's law, we leave that, stick to the exam guidelines. 7.2, it says calculate the distance between R and distance R, that's the distance between the two charges. So we're given the force there, that force. So what we're going to do there at 7.2, we'll say force is equal to K Q1 Q2 over R squared, and then our K, it's a constant as always, and then the R is 5 times 10 to the power negative 9, and S is 6 times 10 to the power negative 9, and then we divide by the distance that is unknown, and then we substitute the force that we're given there, which is 1.2 times 10 to the power negative 3, and then we cross multiply there. So when we cross multiply there, so we're going to have R is equal to 9 times 10 to the power 9 times 5 times 10 to the power negative 9 times 10 to the power negative 6. We divide by 1.2 times 10 to the power negative 3, and we put the square root. Remember, it's R squared there. When we cross multiply, we're going to have this and this square, and then we divide by this, and then we put the square root. So the answer that we're going to have there is 0.015 meter, right? That's the answer that we have, or you can round off that into 0.02 meter, right? The answer can be corrected there as well. Now it says draw a label free body diagram showing the forces that are acting on sphere S, right? Guys, let me show you here. I'm gonna do the force diagram there. We have a normal force. The normal force, guys, you must be careful, it must be perpendicular to the surface. And then we have the gravitational force there, and then we have this tension force. It's a tension force, and then we have the FG perpendicular. That's FG perpendicular, and we have FG what? Parallel there. And we have the electrostatic force, right? The electrostatic force there, which is the force that R exert on S. And then those are the only forces that are acting there, guys. But now when it comes to the free body diagram, guys, you need to be careful. Now, according to 2024, according to the diagnostic report of last year, which is 2023, the free body diagram, it must excludes the component. There mustn't be components there. So let me draw the free body diagram 7.3. So it's an incline like that, guys, right now. It's an incline like that, and here's my charge R, and then I have a normal force, and then I have the FG, which is the normal FG, not the component, and I have a tension force there, and I have an electrostatic force. Those needs to be equal. Electrostatic force. So that's the free body diagram that I need to have, guys. There, these two, they need to be equal because they are both stationary. The S is what is stationary, guys. No? And another thing here, you can't include in the free body diagram the perpendicular and the parallel. You must know that there's a parallel there and there's a perpendicular. But in this here, guys, you do not use the free body diagram with components. Very important. Now let's go to 7.4. 7.4.1. It says calculate the tension, right? Calculate the tension, guys. It's very important. Now, on S, it's only S that has a tension there. It's only S that has a tension there. But remember, on an incline there on the surface, there are three forces acting: this and this, the FG parallel and the electrostatic force and the tension. We know the tension is going to be equal to the sum of these two because they are at rest. So what we're going to say, we'll say F net is equal to 0, and then the forces that are there will choose up the slope as what? As positive. So we'll say tension is positive minus the FG parallel minus the electrostatic force, because they're going down. The electrostatic force is going down and the FG parallel is going down. So you're going to have T is equal to FG parallel plus electrostatic force. As I've mentioned, that it's going to be the same. So you have FG mg sine theta plus the electrostatic force, which is the electrostatic force we already have there. So we'll have here the mass. What is a mass of S? We were told in the statement the mass of S is 0.01, right? 0.01, and then we times by 9.8, and then sine the angle, it was 25, right? 25 degrees plus the electrostatic force is 1.2. 1.2 times 10 to the power negative 3. We were given in the statement. That if you punch that in the calculator, your answer there, it will be when I punch that in the calculator, it will be 0.04. 0.04. It's 426 newtons in the calculator, but since you have to put it in two decimal place, it has to be 0.04 newtons. That's the tension there. Now let's go to the next question. Calculate the net electric field at point P. Now let me erase this. The net electric field at P, that is due to this one and this one. We wanted the net electric field at this point, right? So now what do we need to look at carefully? The electric field that is exerted by R on P, the field lines of R are positive. They're going away, away, away. But the field lines that are parallel to P are going to push P to the right. So when you draw the free body diagram of the electric field of P, of R to P, it's going to go to the right. So this is the electric field of what? Of R on P to that direction, right? And then if you look at the distance from there to there, it's this distance that we calculated plus this. It's a longer distance, so it's going to be smaller compared to this one. Now the electric field lines of S, since S is negative, are going towards. So the direction of the electric field that we experience by P, it's gonna go to the it's gonna go down the slope, and it's going to be bigger, so it's going to be something like this, right? So it's an electric field of what? Of S on P. So that means our net force, our net electric field is going to go down the slope because the bigger electric field is going down, right? So when we calculate it there, it's 7.4.2. So I'll calculate the electric field, the electric field of what? Of S on P. It's KQ over R squared. S on P, it's from here to here. The distance is what? And the charge is 6, okay? So it's going to be 9 times 10 to the power 9, and the distance, the charge is 6 nanocoulomb, and the distance is 0.03 square. And the answer there of that, when I punch that in the calculator, it's 9 times 10 to the power 9 times 6 to the power negative 9 divided by 0.03 square. It's 6 times 10 to the power 4 nanocoulomb. And the direction of that, direction of S on P, I told you it's going down the slope. So it's going to be down the slope. So it's down the slope. And remember, I choose up the slope as positive and down the slope as negative. Down the slope. And then we calculate the electric field of R on P. It's going to be 9 times 10 to the power 9, and then R is 5, right? It was 5, right? Yeah, positive 5. 5 times 10 to the power negative 9. And then the distance, remember, the distance is from here to there. So that means I'll add this R plus 0.03. So I'll say 0.03 plus this distance, which is 0.015. That's the R, 0.015 square. And then when I punch that in the calculator, it will be yeah, the answer here, it's going to be 2,22 2 times 10 to the power 4 newtons per coulomb. And the direction of that, as we mentioned, guys, it's going to go up the slope because it's positive. It's going to go up the slope. So it's up the slope. But guys, when it comes to directions, if you're watching all my videos on electrostatic, you understand what do I mean about the direction that is up the slope. And then we do the E net. The E net is equal to the electric field of R on P plus the electric field of S on P. But their directions are very important. We said the R on P, it's going up the slope, it's going to be positive, and the direction of S on P, it's going to be negative, which is down the slope. So let's substitute the values. So we're going to have the R on P, which is 2,22 times 10 to the power 2 times 10 to the power 4 minus, this is going to be minus what, 6 times 10 to the power 4, and then 6 times 10 to the power 4, the answer there, it's 3,78, and it's negative, times 10 to the power 4 newtons per coulomb. And that negative, it tells us what I've mentioned, that it's going to be down the slope. The net, our net is going to be down the slope, so it's 3,78 times 10 to the power 4 newtons per coulomb, and then the net is what? It is down the slope. Right, I hope that makes sense, guys. Cheers, bye.